Hello. In this screencast, I'll be covering ideal gas law, which in many ways is the cornerstone of our gases unit. Before moving on to what the ideal gas law entails, let's recap yet again what kinetic molecular theory means, since kinetic molecular theory defines the parameters of an ideal gas, and this is, after all, called the ideal gas law. We still assume that all gases in KMT are behaving ideally, which means all masses are almost zero. We call those point masses. Those point masses have no forces of attraction between them, so they have no intermolecular forces, and there are huge spaces between the particles. Since the particles are so teeny tiny, the spaces between particles become really, really significant and important. So in this sample of gas, I have literally two particles of gas inside the box. The space between them is huge compared to the size of each individual gas particle. When the gas particles do move, they always move randomly in straight lines. They are constantly moving. And when they do collide, as they occasionally do, they will experience elastic collisions, so kinetic energy is conserved. Meaning that when they hit each other, they will bounce right off. The kinetic energy of each particle before their collision is equal to the kinetic energy of each particle after they break apart. Finally, the last postulate of kinetic molecular theory is that the average kinetic energy is equal to 3 over 2 times r times t. 3 over 2 and r are constants. So what this means is that the temperature of a gas sample and the kinetic energy of those particles are proportional to each other. And since kinetic energy is equal to 1/2 times mass times velocity, that also implies that mass has to do with the speed and the kinetic energy of a particle. So, at a minimum, kinetic energy is also related to how fast the particles are going. That's our rundown of KMT. Know, however, that you can manipulate conditions to force a gas to act as if it was ideal. So I call this the ideal conditions for ideal gases. So if you want to force a gas to act ideally, you can impose upon the gas two conditions. The first condition is very high temperature, so make it very, very, very hot in there. A very high kinetic energy for those particles means the collisions that they have will be probably elastic. And the reason why is they are traveling pretty fast, since kinetic energy and speed are related. And since those particles are moving really, really fast, they won't have time to form forces because they are bouncing off almost immediately right after they hit each other. No forces means no time to react. Since there is a very high temperature, it's very unlikely that they will have inelastic collision. You would also impose upon that sample of gas a very low pressure. At a very low pressure, the gas volume will be huge. So it will occupy a great deal of space. Therefore, that causes the spaces between the particles to become even larger than they normally would, meaning again that they don't have much forces of attraction between them since they are so far apart from each other. So, what all this means is that gases with a smaller molar mass, things like hydrogen gas, which is the smallest of the gases with a molar mass of 2.016, smaller gases tend to act more ideal because their molecules are literally smaller. Whereas a gas like SF6, which would have a massive molar mass, when they collide with each other, they are more likely to have interactions between them because they're probably traveling slower. Conversely, you can force a gas to act more real, so that would be not following KMT, and that would be if you impose upon that gas two other conditions, which are, as you'd expect, the reverse. Gases are more real at a very low temperature. A low kinetic energy means particles are moving less. If they're moving less, the collisions are more likely to be inelastic because when they approach each other, they have more time to form intermolecular forces. Some of the kinetic energy, when they do collide, will convert to potential energy. So, therefore, the kinetic energy will not be conserved. And since the kinetic energy is not conserved, they probably will react. So, in other words, collisions that are inelastic favor the formation of intermolecular forces between the particles. The other condition for a real gas would be if you impart or impose upon the gas a very high pressure. So, a very high pressure forces the gas volume to be small because those particles will be pushed closer together. So, here's a giant space where you have a very high pressure exerted on the container. So, the gas volume will be small. I should have written it like this. Sorry about that. So, the spaces between the particles end up being small. So, in comparison to the particle size becomes more important and significant. So what that means is that gases with larger molar masses tend to act more real. So in other words, when real gas particles collide, they tend to have intermolecular force. They tend to have collisions that do not conserve energy. So something like SF6, which is a very heavy molar mass of a gas, tends to act more real than hydrogen gas, which tends to act more ideal. So now that we have a little better understanding of what ideal and real mean, let's swing back and take a look at the ideal gas law. The ideal gas law is at its heart a formula. The formula is pressure times volume equals the moles of a gas times the temperature of a gas in Kelvin times a constant called R. Before I tell you about R, just let me tell you that the gas that we're examining in the problem or in each problem is not changing. So we are not changing pressure or volume or temperature or moles. That is very unlike the other gas laws where all of those things were changing, like Boyle's law, and laws where all of those things were changing, like Boyle's law and Charles's law and Avogadro's law and so on. So now let's take a look at this R constant. This constant is called the ideal gas constant or just gas constant. And it does have different values depending upon the pressure of the gas being studied. So if, for example, you were solving an ideal gas law problem and the pressure was given as like 2 atm, that means when you try to search around for an R value to use, you'd have to use 0.0821 for R because the units of R have ATM in it. So choose carefully. If the given pressure is in terms of kilopascals, use 8.314. If your given pressure is in terms of millimeters mercury or torr, you're going to use the value 62.4.